with the expected dimensions. First of all, thank the organizers. Is there any organizers? Okay. Anyway, I want to thank the organizers for inviting me here to present our vision work. So first, I want to introduce my collaborator, Shao Mingjian. This handsome young man. He's extremely brilliant and very broad, and you can see that he's from KIDP and Moore Fellow and Station Q Fellow. You know, he's certainly very, very broad. And I believe that he will be on the job market this year. So if you have a position, please consider him. Yeah, anyway, so the key point in the title will be interacting topological insulators with synthetic dimensions. So I will explain what they mean. Okay, so we all know that we have a very heroic, our field has a very heroic classifications of topological insulators and topological superconductors almost 10 years ago. Actually, it's a periodic table, so they have a classification beyond 1 to 3 dimension. But these higher dimensional topological insulator and topological superconductors, they are very interesting to theorists like me, but actually they are of theoretical interest only. Until very recently. Okay. So actually, so before I introduce the recent experiment, so let me actually review how we can actually realize a higher dimensional topological insulator using a lower dimensional platform. Actually, so this follows from the idea, well, I'm not sure whether this is the first paper which actually used the idea, but this is the paper that I learned this idea. So basically what they did was that they actually basically they take a 2-dimensional chain insulator, for example. This is a simple example, of course. In the simple example, they used a 2-dimensional chain insulator, Hamiltonian, but they build the Ky, the crystal moment along y direction as a tuning parameter. The tuning parameter theta is periodic. And actually, then the chain number in the 2-dimensional chain insulator, actually, if you do the calculation, it actually it's still there. Of course, you can still define the chain number in the space of the x direction crystal moment, and also this periodic theta, periodic tuning parameter theta, and then this d theta over dp will drive a charge pumping from the left to the right in the 1-dimensional system. So this actually becomes a 1-dimensional Hamiltonian with one tuning parameter. So when you tune the tuning parameter through one cycle, you will pump one charge from left to the right, and the charge pumping is quantized, and the charge pumping is going to be proportional to the chain number in the moment and space, and also in the parameter space. Okay, so actually, earlier this year, there was a very nice experiment using this idea. Actually, the claim is that they realized a 4-dimensional chain insulator. Actually, a 4-dimensional chain insulator. The way they do that is that they use a 2-dimensional optical lattice. It's a 2-dimensional physical platform, but they also have like 2 extra tuning parameters. So the extra tuning parameter basically is just a superposition of 2 optical lattice. With 2 different, with a short lattice constant and also a longer lattice constant plus a phase angle here. So this is also a periodic tuning parameter. Then actually in the kx, ky, and also phi x, phi y in the 4-dimensional space, suppose I view phi x and phi y as a periodic tuning, as an extra crystal momentum in periodic, then actually I can define a second chain number here. I can define a second chain number. So this way, the claim is that they realized a 4-dimensional chain insulator. Okay, they realized 4-dimensional chain insulator this way. As long as we build this tuning parameter as a extra dimensional crystal momentum. Okay, so this actually is a very, very easy, very simple idea. And actually, so let me say a little bit more about the 4-dimensional chain insulator. The 4-dimensional chain insulator, the boundary will be one single wire fermion. Okay, so this is the left wire fermion. And there's a no-go theorem, which has been mentioned before in this conference, that it's guaranteed that on the 3-dimensional lattice, if I want to realize the left wire fermion, I will have to realize the right wire fermion as well. So that's why in the wire semi-metal, we'll have to realize both the left wire fermion and the right wire fermion in the same braid zone. But actually, as the boundary of the 4-dimensional system, we can realize a 3-dimensional wire fermion, left wire fermion, on one boundary and realize the right wire formant on the other boundary. Okay, this is basically the physics of the four-dimensional chain insulator. Okay, so the goal of this talk is try to study interacting effects, okay, on the synthetic topological insulator. Oh, by the way, I mean, this is not the only synthetic method, okay? So actually, Condensed people, they have very smart ways of engineering extra dimension. This tuning parameter thing is just one of the several methods of doing a synthetic dimension, but this is my favorite one, okay? This is my favorite one, because actually the tuning parameter is continuous. You can imagine that if I view the tuning parameter as the extra crystal momentum, and it's continuous, this means that this extra spatial dimension is actually infinite, okay? Because actually the momentum is quantized 2 pi over L, L being the size of the extra dimension. So it means that if the tuning parameter, it means that effectively the extra dimension is in the thermodynamic limit. Okay, so that's actually a pretty good advantage of this method. Okay, so our goal is to study interaction effect. Okay, so what do we know about interacting effect in the topological insulator? So this also has been mentioned in previous talks. So we know that at least we know that interaction can collapse the classification or reduce the classification of a topological insulator. So what it means is that without interaction, we may have a Z classification of some topological insulator. But under interaction, the classification may reduce to ZA, Z16, depending on the dimension and depending on the symmetry. So this also means, so physically what it means is that so without interaction, the boundary of the topological insulator is protected to be gapless. Some gapless wire formant, gapless marijuana formant. And actually the symmetry will forbid to generate a master. But under interaction, in some cases, interaction can generate a mass gap, can drive the boundary state into a completely trivial state, fully gapped state without breaking any symmetry, which means that the mass operator will still have a zero special value. Okay, so that's what it means. And another thing the interaction reduced classification means is that in the parameter space, I can tune continuously. So without interaction, this topological insulator and trivial insulator will have to go through a band closing phase transition in the bulk. Will have to become gapless. But under interaction, I can actually go through an adiabatic path. From this side to this side without breaking the symmetry and also without closing the gap at all. Okay, this actually is physically what it means by interaction reduced classification. Okay, so then there seem to be two equivalent things. Okay, so first of all, the edge state can be trivially gapped out by interaction, and second, the bulk topological phase transition can be avoided with interaction. So these two statements seem to be equivalent, although I don't know a mathematical proof for these statements, but they seem to be equivalent and they seem to make sense because actually we have a Topological network picture about the topological phase transition. So actually we can try to construct this topological phase transition by a wire construction or network construction, whatever you want to do. So for example, suppose we have an edge state here. And we have 1, 2, 3, 4 edge states. And suppose actually, and then we turn on tunneling between these wires. Then suppose tunneling between the wire 1 and wire 2 is stronger than the wire 2 and the wire 3. Then these two channels will cancel each other. These two channels will cancel each other. Then the entire system will have no edge state at all. So, however, suppose the hopping between the 2 and 3 is actually stronger than the hopping between 1 and 2, then these two channels will gap out each other. Then the channel 1 and channel 4 will be left out to be gapless. So this system will have a gapless state. So we call this is the trivial topological insulator, and this is a topological insulator or SPT or symmetry protected topological state. And actually by tuning TO and T even, T odd and T even, we can go through a phase transition. And you can see that suppose we can gap out the boundary, suppose actually the interaction can gap out the boundary without breaking any symmetry, then the Topological network model will tell you that the transition between this one and this one will not close the gap. Okay, there's no real phase transition between this one and this one. Okay, these two ends of the phase transition. So this video picture suggests that the two statements I made before, like the boundary can be gapped out without breaking symmetry, and the exist adiabatic curve connecting the two phases seem to be equivalent. Okay. So the first example of the interaction-reduced classification of the topological insulator topological superconductor was actually discovered by Fedotkovsky and Kitaev. It's a one-dimensional example. In one dimension, actually, it's especially nice in the sense that we can use a lot of Gaussianization, reformalization tricks, and actually they constructed exactly what the interaction looks like, which give us this adiabatic path, and they show that there does exist an adiabatic path. For one dimension, we can there's a lot of tools that we can use. In higher dimension, we will have to rely on some argument why this actually happens. But actually, the key point that I hope you can take home from this talk is that with synthetic dimension, the interacting topological insulator with synthetic dimension is fundamentally different from the interacting ordinary topological insulator. It's fundamentally different in the following sense. Okay, so we know that in condensed matter system, we always consider local interaction. Actually, well, if we don't worry about Coulomb interaction, okay, we always consider local interaction. So actually, a lot of so by interaction-reduced classification, I mentioned before, I always meant local interaction. But when we have a synthetic dimension, the situation becomes very different. The reason is that some extra dimension, actually they are synthetic, they are tuning parameters. So it means that in the real physical system, for every tuning parameter value, there is a local interaction in the, for example, two-dimensional real space, Okay? So it means the interaction for every tuning parameter P, there's a local interaction. So this, we just learned that the tuning parameter P is identified as the crystal momentum in the extra dimension. So this means that this interaction will be local in the real physical dimension, but non-local in the extra synthetic dimension. It's actually local in the momentum space in extra synthetic dimension. Okay, so this is the fundamental difference between the interacting topological insulator with synthetic dimension and ordinary interacting topological insulator. Okay. But actually, then this problem becomes very complicated. Okay, because actually, I mean, we always discuss local interaction. We almost never discuss non-local interaction. Okay, but this interaction turns out to be non-local. Question.
Just the problem that you are studying is to study loops in the space of gapped phases. Is that or like higher loops? Is that the problem that you are studying?
Loops,
like non-contractible loops in the space of.
In mathematical terms, probably yes. Right. Yeah. Right. Yeah. Well, anyway, so as I said, this interaction will be non-local in the synthetic dimension. But if we take a closer look, it actually has the advantage that it's still parameterized by the tuning parameter P, which means that it's still parameterized by the crystal momentum. Okay, so this means that we can actually use the dimensional reduction method. Actually, in the papers I mentioned before, to study this interaction. So actually, the dimensional reduction method, like the viewing the crystal momentum as a extra dimension, this trick cannot be applied to a local interaction. The reason is that with the local interaction, momentum will not be conserved at all. So actually, we cannot label a many-body state with a single particle momentum. But here we can, because actually here the Hamiltonian will still be parameterized by a momentum. Okay, so our goal is to study how this kind of a special form of interaction will reduce the classification of a topological insulator. We considered two examples. One example is topological insulator with this symmetry. This symmetry is actually just two copies of a chain insulator in any even dimension, in 2 dimension, 4 dimension, 6 dimension. We always have chain insulator. So this symmetry simply means that we have 2 copies of a chain insulator with actually opposite chain number. But this Z2 symmetry means that one of the chain insulator will have a 0 Z2 charge. The other chain insulator will have a 1 Z2 charge. Okay, we'll have 1 Z2 charge. So the other example we started is the U1 direct product Z2T symmetric TI. So this actually is just a 2 copy to hidden 3B if we are in 3-dimensional space. Okay, we have 3-dimensional space. So this example is more familiar to condensed matter because that's more realistic. It's a hidden 3B, it's 2 copies of hidden 3B. And we know that suppose all the dimensions are physical dimensions, suppose we are in a 3-dimensional physical dimension, then the classification of this guy is reduced from Z to Z8, okay, reduced from Z to Z8. But actually, suppose some of the dimensions are synthetic, okay, suppose some dimensions, so the capital D is the total dimension, including both the physical dimension and also the synthetic dimension, delta, okay, D is the physical dimension, delta is the synthetic dimension. Then the claim, our result is that the classification is reduced from Z, for both cases, classification is reduced from Z to some complicated form like this. Okay, so but it involves delta. Okay, it involves delta. So which means that delta will enter the number of the synthetic dimension will enter the classification eventually. Okay, so how does it happen? So let's just first evaluate, investigate the simple example. Okay, let's just look at a simple example. Let's look at two-dimensional example, which is a non-chiral U1 cross V2 topological insulator in 2 dimension. So this is actually an example which was started before, of course. I mean, without synthetic dimension, it was started before. So this just simply means that this is a chain insulator. This is another layer of chain insulator with the opposite chain insulator. But actually under the Z2 symmetry, the first layer does not change sign, but the fermion in the second layer will change sign. Okay. So the boundary of this state will just be this. Okay, will just a left-moving chiral fermion and a right-moving chiral fermion. But under the Z2 symmetry, the left-moving mode will not change sign, but the right-moving mode will change sign. Okay, so it's very easy to convince yourself that actually we cannot turn on any mass term here, because once we turn on mass term, we will have to mix the left-moving mode and the right-moving mode. They breaks the Z2 symmetry. Okay, so it means that without any interaction, the classification will be Z. Okay, classification will be Z in this case. Okay, and this is the spectrum of the boundary states. But then once we turn on interaction, it was studied by, for example, Gu and Levin. But actually, there are many other papers studying similar system. Suppose we turn on interaction, and turns out we can use the techniques and use the result from the Fidakovsky and Kitav's paper, and we can show that the classification is reduced from Z to Z4. Okay, Z to Z4, which means that suppose I times 4 here, then actually the interaction can gap out this boundary. The interaction can gap out this boundary without generating a mass term at all. Okay, so if I calculate the fermion mass term expression value, it's going to be 0. Okay, it's going to be 0. So right. So one can go through Fidakovsky to have some paper to actually to learn all the techniques, but actually it's slightly too technical to explain here. But actually, so conclusion is that suppose D is 2, delta is 0, which means that there's no synthetic dimension. Okay, all the dimension is physical dimension. The classification will be D4. Okay, but then let's imagine that one of the 2 dimensions is actually synthetic. Okay, let's imagine that well, of course, actually it's going to be a one-dimensional system with a tuning parameter along the other direction. Okay, with the tuning parameter. So the tuning parameter P will actually be along the edge. Okay, will be along the edge because the P1 has to be a conserved quantity. So this means that this figure, the same figure I showed you before, this P will be a tuning parameter. Okay, it means that we are solving the edge state of the one-dimensional system with a tuning parameter P, and actually with one single copy of the system. This actually becomes just a level crossing. Okay, becomes a level crossing. So it means that the non-trivial boundary state simply means that there's a level crossing as the boundary of the one-dimensional system when I tune the tuning parameter P. And this level crossing is unavoidable. Okay, it's unavoidable. Okay, it has to be gapless. The reason it's unavoidable is because actually when P is greater than 0, I mean this part of Hamiltonian shows that the left moving particle, the left particle will have a particle number 1. The right particle will have particle number 0, and on this side, the right particle will have particle number 1, and left particle will have particle number 0. It means that they will have opposite Z2 charge. Okay, these two sides will have opposite Z2 charge. This means that by tuning this P, there has to be a level crossing. Okay, there has to be a level crossing. However, suppose I double the system, okay, I times 2 of the system, then this side will have a 2 left particle, and this side will have a 2 right particle, and then actually these two sides will have the same Z2 charge. Okay, we have the same Z2 charge, so the level crossing can be avoided. Okay, level crossing can be avoided. So indeed, it's the case. We can just design the Hamiltonian. Okay, we can design the Hamiltonian like this. So this just single particle quantum mechanics just can be solved very trivially exactly. Okay. So it turns out that you can see that with this interaction, then actually, so this is the ground state of the edge state, and this is the first excited of the edge state. Actually, they are always gapped out. Okay, they're always gapped out. So this means that for this U1 cross Z2 Ti at D equals 2, when there's no synthetic dimension, the classification will be Z4, but when there's one synthetic dimension, the classification will be Z2. Okay, will be Z2. So it changes depending on synthetic dimension.
So you started with this like two counterpropagating like a 1D physical system, right? With different Z2 charge.
Well, actually, when there is a synthetic dimension, actually, it pretty much becomes a zero-dimensional quantum mechanical problem because actually, I just solved this. I just solved the Hamiltonian for every P.
Yeah, but what I'm asking is, so this entire system is like 1D system.
Yeah, it's a gap the 1D system. The one-dimensional system is the bulk.
Oh, I see.
Yeah, it's like if you tune the one-dimensional system like this, right? So the one-dimensional system is gap in the bulk. So we are solving the boundary system. The boundary state actually looks like this. Okay, the boundary state looks like this. But the boundary state, because P is a tuning parameter, we just solve this zero-dimensional quantum mechanical problem for every parameter P, which can be done very easily. Okay, so now you can see that for this simple example with capital D equal to 2, then actually for different delta we have different classification. So we can actually go to a higher dimension. For example, this actually is a slightly less well-known example. It's D equals to 4. Okay, D equals 4, and actually we have the same symmetry. So this actually means that it's a D equals 4 non-chiral topological insulator. It means that actually as the boundary we have a left wire fermion and a right wire fermion. And under the Z2 symmetry, the left wire fermion still does not change sign. The right wire fermion will actually change sign. Okay, right wire fermion will change sign. So again, you can convince yourself that there's no mass term you can turn on without breaking the U1 and V2. So this again, without any interaction, you should have a Z classification. Okay, without any interaction, you have a Z classification. Okay. Okay. Then what about returnable interaction? So this actually, it turns out, this actually will be a difficult problem because we are studying a three-dimensional Dirac fermion with a strong interaction. This is a very hard question to answer, but actually we can use some argument to actually handle this problem. So it's a pretty standard argument in quantum physics. So this actually is a toy model we started a few years ago. We first break part of the symmetry, and then we try to restore the symmetry by proliferating or condensing the defect of the symmetry, and argue that the defect will be trivial with certain copy. So for example, here we can actually spontaneously break the U1 symmetry and create a U1 superfluid phase, which actually will gap out the entire system. Then we create a U1 vortex line, and after U1 vortex line, by solving the Schrodinger equation exactly, you can show that there is a chiral Majorana fermion flowing along the U1 vortex line. Okay, along the U1 vortex line. And again, the remaining unbroken Z2 symmetry will take the chi left to chi left, and the chi right goes to minus chi right. Okay, so this problem becomes precisely the edge state of the P plus minus IP bilayer topological superconductor with the Z2 symmetry. And actually, we know that this case actually has a V8 classification, which means that for 8 copies of the system, it can be gapped out without degeneracy. So this actually means that the classification will reduce from Z to Z8 for this particular topological insulator in 4 dimensions, because actually I can restore all the symmetry with interaction by proliferating or condensing this vortex line, because the vortex line is fully gapped by interaction without breaking any symmetry. Okay, so so the conclusion, the conclusion is that when delta equals 0, there's a Z8 classification. Okay, so what about when delta equals 1? Okay, let's say one of the direction is actually going to be a synthetic dimension. Okay, so now we are dealing with this problem. Okay, this is still the boundary states. The boundary state still mimics the previous boundary state. The only difference will be that one of the tuning parameter, one of the momentum along the z direction will be the tuning parameter p. Okay, will be the tuning parameter p. And it turns out that this theory, precisely becomes the theory which describes the phase transition between the topological insulator, the trivial insulator in this case. Okay, because the P will actually can be viewed as the mass term at V2. Okay, can be viewed as the mass term V2, and the X and Y become a two physical space. Okay, become two physical space. So because we already know that in this case the classification is reduced to Z4. Okay, this case we already know. Okay, this means that for 4 copies of the system, the phase transition can be avoided. This means that the P equals 0 point can be gapped out without any degeneracy. Okay, can be gapped out without any degeneracy. Okay, so it means that actually we can make connection between higher dimensional synthetic topological insulator to lower dimensional synthetic topological insulator. The trick is that interaction will be a parameter, will be parameterized by this P. Okay, interaction will be fully parameterized by this parameter P. Okay. So using the same trick, we can show that suppose we have two synthetic dimensions. Then actually we can make connection between delta d equals 4, delta equals 2 to d equals to 2, delta equals 1. So you will have the 2 classification. So this means that actually, suppose that capital D equals to 4, capital D equals to 4, for 4-0 case, we have ZA. For 4-1 case, this situation can be reduced to 2-0 case, we have D4 classification. And then for 4-2 case, we can reduce to 2-1 case, so they both have D2. So more generally, we can actually make a relation of chain, a chain relation. So So in general, we can make a chain relation. Okay, we can make a chain relation, which is that the synthetic topological insulator with a 2n and a delta can be reduced to this situation. We can make a chain. Okay, so it means that to know the classification for certain d and a certain delta, we only need to know the element, one element of the chain. Okay, one element of the chain. And to know this one element of the chain, we can use the argument I used before, like for the proliferating the vortex line, or we can use some other argument. Okay, so there are several arguments to argue just one element. Okay, it's always possible. So this is the one particular argument, which actually I think I will skip since I'm a little bit over time. I think it's all right.
Yeah.
Okay, fine. Okay, so I will just go to the conclusion. So yeah, right. Thank you for not replying. But, yeah. Okay. So anyway, so actually, so what I'm trying to say is that although the interaction for the synthetic dimension is very non-local, but because it's a very special non-local interaction, it has so the interaction term is parameterized by the same parameter, which actually which parameterizes the free part of the Hamiltonian. We can use the dimensional reduction trick, and actually we can make a chain relation between the different synthetic dimensions, and then as long as we know one element of the chain, then we know the whole chain of the classification. So this is the conclusion. I only discussed this situation, but this is another situation. But actually, the logic is very similar. Actually. So we have the classification, and you can see that delta synthetic dimension will enter this classification in the final result. And actually, I feel that maybe we have only considered the most boring case of the synthetic topological insulator, because actually we can easily imagine some other exotic topological orders that can be realized in synthetic dimensions that just needs a lot of imagination and creativity. Yeah, so that's something we probably will also think about in the future. Okay, thank you for your attention.
Yes.
So for the experiment that you mentioned, the one by Lowe's, the 4-dimensional quantum holes, what would be the classification?
Oh, that was still D. Yeah, that's still D. Because actually, that chiral anomaly is actually very robust. Yeah. So actually, so the interaction reduced classification we know that even without synthetic dimension, does not happen to all the topological structure, only happens to certain topological structure with certain symmetry. So I mean, that's why we choose these two cases where actually we can show that in linear interaction reduce calcification, but for the chain insulator itself, actually interaction does not reduce calcification.
Okay.
This chain you mentioned, I think this is only for the strong invariants, right? And there are also weak invariants which are not captured by this.
Weak invariant. Yeah, actually I don't know what weak invariant is.
I mean, it means the same thing as the. Maybe we should.
Okay, you mean weak topological structure? Okay. Yeah, I haven't thought about that. Sorry.
I remember any opposite example where the interacting phase classification actually is richer than those of free ones, in the sense that there are some phases which are
Say again, sorry.
some interacting phases which don't come from free phases at all.
Oh yeah, that certainly that comes in here. Yeah, that's something I haven't thought about. Yeah, as I said, we in the first paper we wrote, we only consider probably the most boring case, which is actually we just want to see what's the best understood case. The best understood case is actually the interaction will reduce calcification. We don't want to investigate how that will change with the synthetic dimension. But of course, as I said, many more exotic topological order, more topological insulator may be realized using synthetic dimensions. Yeah.
So when the synthetic dimension is just one, this problem looks
Oh,
very.
it can be many. You can
let's take it to be one. Then this problem looks very similar to the flow kit cases.
For one, actually, I was told it's similar, but actually, experimentally, it's actually adiabatic tuning. It's not a fast tuning. Yeah, right. So for example, in Xiao Liang's earlier paper, actually, it's an adiabatic tuning of a theta to give you a charge pumping. But I was told that there could be a connection, which I haven't fully understood yet. But actually, yeah. So that's I haven't fully understood. There may be a connection, but I haven't fully understood. But actually, there could be many tuning parameters. So there.
Hello?
Yeah, the classification of phase can be viewed as a pi zero of this allowed Hamiltonian space.
Why?
And it looks like what you're here describing is the pi 1 or pi 2 of the gapped system. And I wonder maybe there are some mathematics which give you pi 0 and pi 1, pi 2 all together.
Yeah,
right now the table we list basically just listing pi 0. There may be information of pi 1, pi 2.
Okay, great. Yeah, that's part of the reason I gave the talk here, right? So I hope that some people with equipped with a powerful mathematical machine can actually can make this more formal way.
Just
Maybe last
to
question.
answer one question. Yeah, it is. It just take this whatever K theory or cobordism, which classify and just consider it sort of a point.
Yeah.
Consider the parameter space, the same cohomology of the parameter space that gives you, like it's a circle. They have just one parameter in a circle. Just take, let's say, K theory or cobordism of a circle. It's going to give you classification of interacting phases.
Okay.
Families of interacting phases.
Okay, let's maybe thank Cenke again.